Okay, so let us talk about microflow sensors. Microflow sensors are another important component in a typical microfluidic system, and they are used to measure flow rates in microfluidics. Okay, and these microflow sensors can complement microvalves and micropumps in a microfluidic system. Micro pumps are used to generate flow rates, and microvalves are used for controlling flow rates, and microflow sensors can measure the flow rate and check whether the micro pump or the micro valve is performing according to the requirement. Okay. So, we talk about microflow sensor. Okay. So, the microflow sensors are important component in microfluidic system. Okay, and they are used to measure flow rates, and they can complement micro pump or micro valve in a control loop. Now, what are the advantages of microflow sensors? The advantages are that these microflow sensors are miniaturized in size, so they consume very less power, and the second advantage is that microflow sensors enables measuring flow rates of the order of nanoliter per minute to microliter per minute, okay, which may not be possible otherwise. So, the advantages are smaller size, so that gives low energy consumption, and the second is they can measure small flow rates of the order of nanoliter per minute to microliter per minute. Okay. Now, let us look at some of the performance parameters of a microflow sensors. The first performance parameter that we will look at is the operational range. Okay. In what range of flow rates a certain microflow sensors can be used. So, we look at few performance parameters. The first parameter that we are going to look at is the operating range. So, operating range is the maximum and minimum flow rate a microflow sensor can measure. And this would depend on the geometry of the sensor, sensor material, and as well as the principle. Okay. The second parameter is sensitivity. And sensitivity is defined as the change in the output voltage for a given change in the flow rate. Okay. So, the sensitivity is defined as S is defined as dV over dq. Okay. Now, this is for a linear case when output is linearly dependent on the flow rate. For a non-linear case, we can define sensitivity at 0 flow rate, and this is called 0 sensitivity. S0 is defined as dV over dq, and that is at q equal to 0. Okay. The third parameter is the response time. Response time is the time taken by the flow sensor for its signal to stabilize once there is a change in the flow rate. Okay. So, this is the time taken by flow sensor to obtain a stable signal after flow rate changes. Okay. So, and the last parameter is the power consumption. Power consumption can depend on the principle of the sensor and also the type of sensor. So, the principle and type of sensor. Okay. So, because of miniaturized size, the sensors have miniaturized size. So, typically microflow sensors will operate using energy of the order of milliwatts. Okay. Now, let us look at what are the different types of microflow sensors. The types of microflow sensors. They can be broadly classified into non-thermal sensors and thermal sensors. Okay. And in non-thermal sensors, they will be based on different principles. One is the differential pressure flow sensor. Second one is the drag flow sensor. The third one is the lift force sensor, lift force flow sensor, and the fourth one is Coriolis flow sensor. Okay. So, these are 4 types of non-thermal sensors. In thermal sensors, we would have hot wear and hot film, and we would also have calorimetric sensors, and we would have time of flight. Okay. So, we will look at each of these different types of sensors. To start with, let us look at the differential pressure flow sensors. So, let us look at differential pressure flow sensor. So, in typically in microflow sensors, the channel sizes are small. So, the hydraulic diameter is small, as a result the Reynolds number are small, which leads to laminar flow. Okay. So, in microflow sensors we have laminar flow. So, in laminar flow the pressure drop delta P can be written as F Re into eta L over 2 dH square into U. Okay. So, that is the expression for pressure drop in case of laminar flow in a micro channel, and FRE has a for a rectangular micro channel, which is the channel cross section that we use quite often in microfluidics. The FRE value is between 50 to 60, okay. And this is the hydraulic dia, and this is viscosity, this is the length scale, this is the length of the channel, and this is velocity, okay. So, what we see here is that the pressure drop is linearly dependent on flow velocity or the flow rate, okay. So, that is used to develop differential flow sensors, okay. So, we actually measure the pressure drop, and from measuring the pressure drop we predict the flow rate, okay. So, the pressure drop delta P is proportional to Q, and so delta P is measured using pressure sensor, okay, and from there Q is predicted, okay. Now, one important thing to notice here is that one parameter that depends on the temperature is eta, okay. Eta is the dynamic viscosity which depends on temperature, okay, and since the dynamic viscosity is dependent on temperature, the flow rate will be affected by change in the temperature. So, many times this differential pressure drive flow sensor are integrated with temperature sensors in order to compensate for the temperature change effect, okay. So, here the dynamic viscosity is temperature dependent. So, the microflow sensors are integrated with temperature sensors for compensation, okay. And based on the principles, two principles that are used to measure the pressure drop. So, two principles used to measure delta P. One is capacitive and the second one is piezo-resistive, okay. So, these two principles are used to measure pressure drop, and from there flow can be predicted, okay. Let us first look at capacitive type pressure flow sensor. So, we look at capacitive type pressure flow sensor. So, as you can see here, this is the inlet, okay, and this is the outlet, and here we have a capacitive type flow sensor. So, as the flow goes in through the microfluidic channel, here we have a membrane, okay, and this is a membrane on which one electrode is positioned, and there is the second electrode here, this is a static electrode, okay. And as the flow rate changes, so does the pressure drop. So, and since the pressure drop is modified, the pressure inside this chamber is changing, and when the pressure changes, there is this movable membrane moves with respect to the static electrode. So, there is a change in the capacitance that happens, okay, and that change in the capacitance is related to the flow rate. Okay. So, here in the capacitive pressure flow sensor we have different components, we have a membrane and we have a counter electrode. So, membrane itself has one electrode, the counter electrode which is typically fixed, and what happens is the pressure causes the membrane deflection. Okay. The pressure causes the membrane to deflect and the membrane deflection will cause change in the capacitance. Okay. So, we can write down the expression for capacitance which is epsilon 0 epsilon r A into D. So, this is permittivity of free space, this is the dielectric constant of the medium which is present between these two capacitor plates. A is the capacitor area and D is the gap. Okay. So, this gap D actually changes when there is a change in the flow rate. Okay. So, what is going to happen is there is going to be a change in the capacitance because of the change in the gap. So, this will be del C over del D into delta D. So, del C is going to be minus epsilon 0 epsilon r into A into del D over D square. Okay. So, that is how the capacitance is going to be related to the gap which is a function of the flow rate. Okay. So, delta C is related to D which is related to the flow rate. So, that is the principle based on which the capacitive pressure flow sensors work. Now, let us look at the piezo-resistive pressure flow sensors. So, look at resistive pressure flow sensor. Okay. So, similarly here we have flow rate Q coming in and is going out, this is a chamber. So, as flow rate changes the pressure drop is going to change. So, the pressure inside this chamber is going to be modified. So, if the pressure modifies the membrane is going to expand. Okay. If the pressure increases, for example, the membrane is going to expand, and because the membrane is expanding, the resistance between these two electrodes R is going to change. Okay. So, that as flow rate changes the pressure changes, and because of the change in the pressure there is a deflection of the membrane for which the resistance R between the two electrodes will change, which is a function of flow rate. Okay. So, when the strain phi is applied, so we would have change in electrical resistance. Okay. So, change in resistance. So, this delta R. So, this delta R over R is going to be a function of strain. So, let us say alpha into phi, and this alpha is the piezo resistive coefficient, or for a strain gauge it is the gauge factor, okay, and phi is the strain. Okay. And typically if you have a strain gauge, then the longitudinal gauge factor for metals is typically 2, and for polysilicon it is 10 to 40, and we have crystalline silicon is going to be between 50 to 150. Okay. So, by measuring the change in the resistance over original resistance will be related to strain, which is related to the flow rate. Okay. So, that is how the piezo-resistive pressure flow sensors work. Okay. Now, let us look at drag force flow sensors. So, let us look at drag force flow sensors. The drag force flow sensors work on the principle that we would introduce an obstruction like a cantilever structure into the flow field, and when the flow rate would change, the drag experienced by the cantilever is going to change. Okay. And by measuring the drag, the change in the drag can be used to predict the flow rate. Okay. So, in a drag flow sensor, the flow measured by measuring the drag force experienced by an obstacle, okay, experienced by an obstacle in a flow. For example, a cantilever, as you can see here, if this cantilever structure is exposed to the flow that is coming in, so what is going to happen is this cantilever structure here is going to experience a drag, okay, and that drag force can be measured by measuring the bending of this cantilever beam, and by measuring the drag we can predict what is going to be the flow rate. Okay. Let us say, and that obstacle could be, for example, an cantilever. Okay. Now, if you assume laminar flow, let us say we are talking about laminar flow, which is often the case in microchannel, then the drag force will be experienced along the direction of the flow. Okay. So, the drag force is going to be, so F1 will be C1 into L eta q dot divided by Ag. Okay. So, here this is the flow rate, this is the viscosity, dynamic viscosity, and this is the length scale, and this is the gap around the obstacle, this is the gap around obstacle. So, in this case this gap that you see here is going to be Ag, okay, and C1 is going to be a constant, this is a constant that depends on the form of the cantilever, So, its length to width ratio is going to determine this constant C1. Okay. So, this is viscosity and this is the length scale. Okay. So, this is the length. Okay. Now, if in addition to this drag force there will be another drag force, okay, because of the pressure drop that occurs across the cantilever. Okay. So, due to pressure drop in the gap, we would have an additional drag force So, and that drag force F2 is going to be C2 rho over A0 Ag into q square, okay. And where A0 is going to be the surface area of the obstacle, and C2 is a constant, rho is the density of the fluid, okay. So, you can find the total drag force F will be F1 plus F2, and so F is C1 L eta q divided by Ag plus C2 rho over A0 Ag square, there is a square missing here, into q dot square, okay. Right. So, this force, the drag total force has two components, one is a linear term, okay. So, this drag force depends on linearly on the flow rate, and the second one is the quadratic term, okay. It varies as q dot square, and when the flow rate is low, the linear term is going to dominate, okay, and then in that case the drag is going to be linearly dependent on the flow rate, and when the flow rate is very high, the drag is going to be dependent on the flow rate following a quadratic function, okay. So, at low flow rate F varies as q dot. So, this is linear characteristic, okay, and high flow rate. So, at low flow rate this term is going to be dominant, and high flow rate this term is going to be dominant. So, this will vary as q dot square. So, this the sensor will have quadratic characteristic, okay. So, with that let us talk about lift force flow sensor. So, let us talk about lift force flow sensor. So, this lift force acts in a direction perpendicular to the flow direction, normal to the flow direction, as opposed to the drag force which occurs along the direction of the flow, okay. And the lift force sensor, based on the principle that as the flow rate increases, the lift induced to an aerofoil kind of structure is increasing with the increase in the flow rate. So, this is the kind of structure we have. There is a flap kind of structure, okay, and when there is no flow, this flap is going to be perfectly horizontal, and when there is flow due to lift force, the flap is going to be lifted on one side. So, this is going to be twisted, and so that lift force is going to be measured by measuring the bending of the beam, okay. So, this beam is hinged around here, so there is going to be bending. So, by measuring the torsional stress, we would be able to predict what is going to be the lift force. So, that lift force will be related to the flow rate, okay. So, what is going to happen here is that lift force which acts perpendicular to flow direction is, so FL is going to be CL A into rho into u square over 2, okay. So, u is the flow velocity which is related to the flow rate, and CL is the lift coefficient, okay. A is the surface area and rho is the density. Okay. So, what we have here is like an airfoil structure. We can have a rectangular plate or a flap, and it will be suspended by two beams. So, as you can see here, so the lift force which is proportional to the flow rate would tend to bend the beams. So, what we can measure is the bending stress or torsional stress, and by measuring the stress we will be able to predict the lift force which will be related to the flow rate. Okay. So, that is the principle of operation of the lift force flow sensor. Now, let us look at Coriolis flow sensors. So, let us look at Coriolis flow sensors. So, the Coriolis flow sensors are based on the principle of Coriolis concept. Okay. So, as you can see here, this is the U-shaped bent tube, okay, and the flow is getting in there. So, this is a mass flow rate sensor, some mass flow rate m dot is going inside the tube and coming out there, right, and this tube is going to oscillate up and down. Okay. So, this tube is going to, so there is a U-shaped bent tube and this tube is going to oscillate up and down as you can see in the image. Okay. As the tube oscillates up and down, it is going to get a bending in the other direction, okay, that is known as the Coriolis force. Okay. So, as you can see here, the tube is hinged around here, there is mass flow rate m dot going in, m dot coming out, and this tube is going to move up and down at some frequency, and when it does so there is going to be Coriolis force developed in this direction. Okay. So, the beam is going to experience Coriolis force in this direction, okay, and that Coriolis force is related to the mass flow rate. Okay. So, this is based on the Coriolis concept, and we have a U-shaped tube, and the U-shaped tube is fixed at two ends, okay, and it oscillates up and down. Okay. It oscillates up and down. So, in that case we would have a twisting Coriolis force that acts on the tube, and that Coriolis force F is given by 2 into m dot into omega. Okay. So, the m dot is the mass flow rate and omega is the angular frequency of oscillation. Okay. So, by measuring this twisting Coriolis force, which can be measured using a force transducer, we will be able to predict m dot knowing the angular frequency of oscillation. So, that is how the Coriolis mass flow sensors work. Now, let us move on and talk about thermal flow sensors. So, thermal flow sensors basically utilize the effect of flow rate on a hot body. Okay. So, the different concept different principles that are available. So, let us look at that. So, let us look at thermal flow sensors. So, here the basically the flow energy is converted into electrical signal, and it considers effect of flow on hot surfaces. Okay. So, there are different principles available. One is the hot wire sensor, the second one is the calorimetric sensor, and the third one is the time of flight sensor. Okay. So, first look at the hot wire sensor. So, let us look at the hot wire sensor. So, the hot wire sensor basically measures effect of flow on a hot body, and we are talking about forced convection. When there is fluid movement. So, what is going to happen is, if you have a constant heat flux coming onto a surface, and if the flow rate is going to increase, then the temperature is going to go down at a constant heat flux. Okay. And if you are trying to maintain the surface at a constant temperature, then the heat flux has to go up with increase in the heat flux. So, there are two things that can happen. One is at constant heater temperature, the heating power or heat flux will go up, or at a constant heat flux or heater power, the temperature of the surface is going to go down, right. So, the heating power can be expressed as heating power P is Nusselt number into conductivity into area of the heater delta T divided by L. Okay. So, this is Nusselt number, this is thermal conductivity, and this is the characteristic length scale. Okay. This is the heater area, delta T is the temperature difference, and for laminar flow we have an expression for Nusselt number, which is square root of Re into Prandtl number to the power 1/3. Okay. So, by knowing the heating power, we can calculate Nusselt number, and from the Nusselt number we will be able to calculate the flow velocity. So, we can predict what is going to be the flow rate. Okay. So, that is how the hardware sensors work. Now, let us look at calorimetric sensors. So, the calorimetric sensors work on the principle that if you have a hot surface and a hot body and flow is coming from one direction, the temperature distribution upstream is going to be different from that in the downstream. If there is no flow, the temperature profile is going to be symmetric about the hot body, but if there is a flow, the temperature profile is going to be asymmetric, and this asymmetric temperature distribution is going to be exploited to predict the flow rate. Okay. So, as you can see here in this image, here we have a heater of length LH, and the upstream sensor is located at LS from the center of the heater, and the downstream is located at a distance LS. Okay. So, on both sides we have two sensors, temperature sensors, and flow is coming in. When there is no flow, the temperature profile is going to be symmetric, and when there is going to be flow, the temperature profile is going to be asymmetric. Okay. So, this is here the channel cross section is given, Ly and Lz are the lengths of the channel, and this heater is located at the center of the channel height. Okay. So, it is basically based on the asymmetry of the temperature profile around heater placed in a flow field. Okay. And this is going to be, the asymmetry is going to be modulated by flow rate. Okay. So, when you have 0 flow, when nothing is flowing, then we have symmetric temperature profile, the temperature profile symmetric, and when you have flow, with flow we have asymmetric temperature profile, okay, between upstream and downstream. Okay. And we would have two temperature sensors, to measure upstream and downstream temperatures. So, that would give us flow rate. Okay. So, the difference in the temperature between upstream and downstream, delta T, as a function of the velocity has been estimated as T0 into exponential gamma 2 into Ls minus Lh by 2 minus exponential gamma 1 into minus Ls plus Lh by 2. Okay. So, this is the expression for the temperature difference between the upstream and downstream. Okay. this is the temperature difference between upstream and downstream. We have an expression for this T0, this is the temperature defined below. 1 is for upstream and 2 is for downstream, as you can see here. So, this is going to be 1, this is going to be 2. So, in that case the expression for gamma 1 2 is estimated as u plus minus u square plus 8 a square over L z square root divided by 2 a, okay, where a is the thermal diffusivity, which is K over rho. So, we can define T0 as follows. So, this is the heater power divided by 8 K Ly into LH divided by Lz plus A into K into gamma 1 minus gamma 2. So, this is the expression for the temperature T0, okay, and this area of cross section is going to be Ly into Lz, okay. Everything else is defined here. So, what is going to happen is we are going to measure the temperature difference, and all the values on the right hand side will be either a fluid property or a flow property, okay, or depends on the geometry, the locations of the heater with the sensors with respect to the heater and the geometrical parameters. So, by calculating left hand side and right hand side, we should be able to predict what is the value of u, okay. So, delta T is measured and right hand side calculated except u. So, we can measure, we can predict u, okay. So, predicting u we can predict the flow rate. So, that is how the calorimetric sensors are going to work. Next let us talk about the time of flight sensors. So, let us talk about time of flight sensors. So, this is based on time taken by a heat pulse to travel through a fluid, okay. So, we have an analytical solution for this. So, T x t, which is a function of time, is going to be q0 dash 4 pi k into t into exponential minus x minus ut square divided by 4 at, okay. So, the temperature is going to be a function of x and t. This is the heat flux that is generated by the heater, k is the thermal conductivity, t is time, and u is the velocity, x is the direction in the x direction, a is the thermal diffusivity, okay. So, we can define a parameter called time constant. So, this is the time at which the signal would pass through the temperature sensor, okay. So, we basically measure the time of flight of the heat signal, okay. So, the time of flight is measured Okay. Now for this to happen, we have to make sure that the diffusive flux. So, you have to ensure that 4 A into T will be less than the heater sensor distance. Okay. So, 4 A AT is the diffusion length scale. Okay. So, in this case what we mean by this is that forced convection dominates over diffusion. Okay. So, we have a point heater which is generating some heat, and we are locating a temperature sensor at some distance, and we are saying that before the heat goes by diffusion, the fluid flow actually carries the heat. Okay. That is what we mean by the diffusion length scale reduce is less than the heater sensor distance. And when diffusive effect is considered, so here the diffusive effect is negligible. When diffusive effects considered, then the time scale tau will be minus 2a plus 4a square plus u square L square over half divided by u square, and that is for u not equal to 0, and when u equal to 0 this is going to be L square over 4a, okay, when u equal to 0. Okay. So, by measuring the time that it takes for the heat pulse to reach from the heater to the sensor, we will be able to predict what is going to be the flow rate. That is how the time of flight flow rate sensors work. Okay. So, with that let us stop here.